Hello, welcome to Engineer Versus. This time we will be versus river, lake, and ocean water cooling. We're going to follow up to the introduction. So, to follow on to this introduction, we have the overview of what the basics are, which we're going to cover here. Then we're going to be talking about beyond the basics, the challenges. Then we'll talk about projects and details in the summary. So, basics. What's to be gained? Why bother? Why are we doing this? So if we hop over to that, we can see that water is the big thing. So to go through this, water can remove more heat, kW per hour or BTUs per liter or gallon than any other fluids, basically any other substance on the planet. Nothing's been invented that's going to be better at removing heat. We're used to working with water. It's non-caustic for the most part. It doesn't have big issues when we're working with it. And because of that, engineers, scientists are used to using it for heat transfer applications. It has been the best medium for centuries, you could even say millennia, for transferring heat. So water becomes very plentiful. It's a very good resource for us to use. So the United States, a few more facts about this. The United States uses about 80% of its water for irrigation, which is 30% or more of the end source, and 50% for thermoelectric. So not all of this is end source. This is pass through when we're making that thermoelectric power. So this is, if you think about hydroelectric dams or anything like that, if you want to think about Lake Mead, that's also one of the sources of electricity that we have today. It's being passed through there. And then another stat here is only about 3%, 2.5 to 3% of the water on Earth is fresh water. So 97% is salt water. That may seem alarming. However, this is pretty much true since ever that we're aware of. Now, some of it, of this 3%, 2.5 to 3%, it's going to be fresh water. We're looking to protect a lot of that. And the idea is, okay, we've got a lot of surface lakes, but this also is, this freshwater estimate is also based on water that's underground as well. We're tapping a lot of that to use for farms and so on, especially if you consider places like China or Uzbekistan or Russia or all sorts of places where the lakes are starting to dry up a little bit faster, and we're starting to tap that underground water, that fresh water that's underground for us. All right, so water for cooling applications we've been using forever, but today we're using seawater directly for seawater air conditioning, called a SWAC system if you want to use that term. Essentially, that's just using water to cool. We'll talk a little bit about that, which is essentially the idea that we're looking at with ocean water cooling. But Hong Kong and other places are already using systems like this. Then there's ocean thermal energy conversion, so OTEC. OTEC's been used or been proposed by a lot of nations, a lot of island nations, and a lot of places. But because of the components that go with it, the manufacturing, the reliability, everything that goes in this system, it ends up being very costly. And it actually is cheaper for a lot of island nations and even say Hawaii to go ahead and import oil, import natural gas for fuel, and run a power plant from that as opposed to putting in an ocean thermal energy conversion system. Now, how this works essentially is it works on a temperature difference. So that temperature difference is where you're getting your overall energy production. So your electricity production is based on that thermal difference, and that can be very small. So you need to go large on these systems in order to even start to make them worthwhile. Industrial cooling, mostly what we're copying or what we're looking at when we're looking at these systems, and it's for waste heat removal. And this waste heat removal can be for power plants, a number of other cycles. But if you have an industrial facility, they have a processing plant, they're making widgets of some sort. They might have a heated process in which they might be allowed to use a certain amount of river water or lake water per day, per week, per month, per year, as long as they don't take out too much of the percentage of what they're looking at from the source and dumping it in at too high of a temperature. The same follows with power plant cooling. So they're looking at cooling power plants, whether it's coal-fired or natural gas. we're looking at cooling those processes down so we can go on to the next thing. Liquefied natural gas process cooling. Rivers and lakes and ocean water can be the sink or the heat sink as far as producing liquefied natural gas. If you think about this, to liquefy it, we need to cool it a lot. And this is becoming more and more prevalent as we produce more and more natural gas, and we're producing it for export as well out of the United States. On the other end, whenever we get that liquefied natural gas there, we want to transfer it back into regular natural gas because it is gas after after all, and that means adding heat. So we're at least trying to, capture that cooling process further down the line. Chemical process cooling, this is, goes along with all the chemical and industrial engineers are using rivers and lakes for that chemical processing. And this again is the same sort of procedure. You have a chemical process that's going to need to be cooled just like a power plant needs to be cooled before it can go on to the next step in the process. So that chemical process cooling can be done that way. Data center cooling hasn't been too popular yet, but it's starting to gain traction as well. Aquaculture and mariculture, that's basically paying attention to all of the thermal processes as it relates to the overall performance of the rivers, lakes, and the ocean. All right. Oh, I have this diagram here on the lower right. Essentially, this is looking at a building where we need to remove the heat. And with this particular one, we have 1,000 tons of heat we need to remove. It's taking it out by pushing in 8 degrees Celsius water. We have 13 degrees Celsius coming out. So you can see it's a 5 degrees Celsius difference here. So if you want to think of that in easy terms in the United States, it's about 10 degrees Fahrenheit. Not too exciting as far as being the most efficient process, but this is just a simple diagram. That heat is then moved into a heat exchanger, and this is where we have our first pass at cooling. Here we have about 7 degrees Celsius coming in, so you can see that this is a 6-degree delta T on the Celsius side. So that seawater is first pumped through this heat exchanger. It picks up some of the heat into the seawater, and then this seawater is then pumped through the condenser water on a chiller unit. Now this chiller unit uses electricity. Essentially, it's using power and a refrigerant to drop this temperature of this water right here, this loop, even further, all the way down to this 8 degrees Celsius. So that's why we have the evaporator and condenser. Then this heated water here goes back out to the sea. Now this chiller is likely going to be targeting that 8 degrees Celsius, so you can have a nice predictable temperature that's going to go in. And why do you need that? Why should we do this? Oh my goodness. Well, the idea is we're having air conditioning no matter where you're at, Western Hemisphere, North America, or Eastern Hemisphere, Northern or Southern Hemisphere, it doesn't matter. We're air conditioning all over the world, and these are the target temperatures that we're typically doing it for. And that's not just for comfort cooling, that's also for dehumidification. If you have too much humidity, you have mold, you have Legionella, you have all sorts of other issues that can go with that. So reducing sickness and increasing health and quality of life has been sort of this big predictor on the air conditioning. Okay, moving along to mechanical cooling. How are we going to do this? We're going to look at a typical system, then we're going to look at a sea or lake water cooling system, and then we're going to do an efficiency comparison. So the first up is a typical mechanical cooling system. So number one, chilled water removes heat from air streams via air handling units, and they basically have chilled water coils somewhere in here. And what I can do is bump this up so we can see a little bit more of that. It's up here somewhere in this system. It's taking heat out and it's putting it into this chilled water system. Then that pump goes through either this chiller, which is indicated here, or the heat exchanger on the left. Now, that chiller or heat exchanger removes the heat from that water and supplies 45 to 55 degree water, somewhere in that target zone, again for dehumidification. And that's where basically this water comes back, it gets pumped back through and either comes here and goes back out as chilled water if it can hit the temperature that it needs to, or this valve closes and this valve opens and it goes through the chiller, and this chiller then cycles it through and pumps it back out as chilled water. Again, 45 to 55 degree target there. Now in this chiller or the heat exchanger, they throw the heat out. So you can see the chillers pumping this condenser water out here, and this heat exchanger is also doing the same thing. And basically, they meet up at this particular line right here. Even though the temperatures might be a little bit different, the idea is that this heat exchanger has valves to see how it will operate. This chiller expels this warmer temperature condenser water. That's the water that's on the hot side of the chiller. And this pump basically drags it through the chiller and then sends it out to a cooling tower. This is where you're going to look at buildings, say outside. You're going to notice that on top or beside the building, there's something running and it might be expelling this heat that was gained clear back here from the air handler. It passes through the chiller, it passes through all the pumps, the heat exchanger, and then out to this cooling tower. And that cooling tower then expels that heat to the atmosphere. So all these processes are stepping. Each step takes you have a loss of efficiency. And not only that, you can notice that it's going to take electricity for the chiller to run. You have electricity for the pumps to run, the chilled water pump and the condenser water pump, and then also electricity to run the fan, the motor for the fan of the cooling tower. All right, well, let's look at a sea or lake or river water cooling option. Essentially, the chilled water system that we have with that remains the same. We have a coil in an air handler or somewhere out into the building. It's taking heat out of the system. That pump is basically the same size, but instead we have a heat exchanger here that might be a little bit bigger, something that's sized to handle 100% of that load. Now that heat exchanger is exchanging and getting rid of heat to that seawater that's coming in. And after that does that, it can pass right back out to the system. So this pump is just a circular pump pumping straight out back through the system. Now, what happens with the seawater after it's drawn in, it goes through this heat exchanger, is it's pumped back out. And this is where the pump for the condenser water, the seawater pump comes in to handle that. And that flow then goes out at a higher temperature. Now, again, what we're looking at is this is about a 10-degree temperature difference, 10 degree Fahrenheit, about 5 degrees Celsius, using those rough numbers for that. Essentially, it's going through that cycle, single pass. There's no dual pass, but it's very easy, very predictable, and you can start to size both sides of the system based on the flow and the temperature changes. This is very, very simple, and not only that, it's really much easier to maintain. So let's just compare the efficiencies before diving into all those other tertiary items. Efficiency, traditional cooling per megawatt. So the idea is per megawatt that we're taking out of a building, this is what we're boiling everything down to. Now the chiller efficiency, we have at zero point 0.4 kilowatts per ton. So per megawatt, we have about 0.12. So that's how much energy we're going to use to take out a megawatt of heat. So that's how much the chiller is going to be using. It's 0.12 megawatts. Cooling tower efficiency is around 0.08. Now, the thing about cooling tower efficiency that I'm not getting into on this particular lecture is that the cooling towers are going to be beholden to the location. And why? Because the more moist it is, you're changing your different temperatures outside, your cooling towers are going to behave very differently. And this is where the efficiencies of the cooling tower can vary depending a lot on your locations. Anyway, we translate that into the amount of energy, and we have 0.025. The chilled water pumps we're putting in at about 0.025 also. Condensed water pumps are about the same. And we're saying that those operate for all year long. Now we add all of those up and we get 0.64 kilowatts per ton, adding up all these different kilowatts per ton, and that is about 0.195 megawatts per megawatt of load that we have. So you can see how much energy we're expending per megawatt of load. So this is required per megawatt of tech load. Now tech load, all we're saying is just technically how much load do we have in a building that we need to remove. So that load might be coming from people, that load might be coming from outside, the sun, or might be coming from equipment that's inside or an industrial process. So per megawatt, again, we're looking at almost, zero point 0.2 megawatts per megawatt of load. All right, so the sea, lake, river water per megawatt, again, we'll have the same number, same amount of chilled water circulation pumps. So that does not change. The lake or seawater pumps, we are estimating that it's going to be twice as much. This is a gross exaggeration, by the way. So the amount of flow is more likely to be around that of the chilled water pumps. But what we're doing here is we're saying maybe we have to pump it further. Maybe we have other issues that we need to worry about. So we're going to throw a safety factor in here, and that's where that safety factor is. And now that total for us is 0.24 kilowatts per ton. And it's, again, if you total this up, it's about 0.075 megawatts required per megawatt of technical load. Again, load for the building. So you can see how this is already a lot different. And the other thing I wanted to compare against is, okay, we've got this kW per ton numbers, 0.64 and 0.24. The reason I have this chart right here is to see where that compares so that you don't think that this is some sort of very inefficient plant. Basically, this is a new technology plant in here, 0.64, new technology, all variable speed, all new equipment, all very, very high efficiency operation. So this is in the excellent range. It is not in the high efficiency or optimized or new here. And it's way better than something that you might say is been operating for some time or is an older system, say 10, 12, 15, 20 years old. That's probably where you're going to fall, is that needs improvement to fair, just because there's been leaps and bounds during that time in the chiller efficiencies, as well as the overall system efficiencies and how we're operating and controlling. So we compare this really efficient traditional cooling against a lake or seawater, and you can see that the lake or seawater isn't even on this chart as far as a kW per ton. All right, so really much more superior. And the difference is down here in the savings is 0.4 kW per ton difference. The savings here per megawatt is 0.135 megawatts per megawatt. So this is all savings numbers again. So what we're doing is taking that 0.135 and multiplying it by the number of hours a year, just as a gross sort of summary. So this is the number of hours per year in any given year, and we're saying, okay, we just multiply that out and we get over 1 million kilowatt hours a year. So let that sink in for a moment and just think 1 million kilowatt hours per year is what we're looking at as far as the savings. And then on top of that, we are doing freshwater savings by over 1 million gallons a year also. Now, this is a harder number that I'm not including here in this particular lecture to keep it shorter, but it can be definitely, you can dive into this and what your cooling tower is going to be operating at, and this is what is going to be consuming all that fresh water, all that water that we're talking about as far as freshwater consumption. So a quick analysis revealed 1 million to 2 million gallons of water per year per megawatt. So we'll pick up in a moment with the next step, and that's finding water temperatures that we can use.